Hello comrades, welcome back. Today we are going to build our way towards finding the derivative of inverse functions. But before we do that, we need a strong recap of what an inverse is, both algebraically and graphically. So let's say I have this friendly fella here in the coordinate plane, nice friendly function fella, looking like that. Actually, let me make this a little sharper. And let's say I would pick this point here. Let's call that point AB. AB. It's a function, right? Kind of like an exponential. Now, if I were to take AB and invert it, where does this point get mapped to? Where does it get sent to, so to speak?
It'll be sent to the point BA.
Yes, it'll be sent to the point B. Let's do this in blue. BA. Likewise, this point, that y-intercept, that gets sent to.
It gets flipped over the x-axis. Oh, it's on the x-intercept.
Yeah, that just becomes the x-axis. So if I were to do this process of inversion for every single point on the original function in black, what is, and because this is a symmetrical process, what is the equation of the line of symmetry between these two?
Y equals x.
Yes, sir, y equals x. So anytime you have an original graph, an original function, or any kind of graph, to find the inverse of that graph, you just reflect it across the line, y equals x. Now, this particular inverse graph, this inverse relation, happens to also be an inverse function, because it passes what test? Anyone remember?
The vertical line test?
Yes, vertical line test. Passes the vertical line test, so this inverse happens to also be an inverse function, and inverse functions are what we are going to focus on today. First part is, how do we know that a given function has a corresponding inverse function? Well, to build up to that, we're going to talk about this term called injectivity. Inject. It means the same thing as one-to-one. Do y'all guys remember from algebra and pre-calc? Okay, good. So a function is injective. So let's say f of x is injective. If the following holds true. So it's just a definition of injectivity. If you pick two y values on the graph of f, let's say f of x1, f of x2. If you pick two y values, f is injective, it's one-to-one. If what is true about x1 and x2?
And x1 equals x2?
Yes. So this is just the algebraic definition. But what this is saying graphically is that for any two y coordinates you pick on the graph of f, if those two y coordinates are the same, then the x coordinates that go with them also have to be the same. Does that make sense? So, for example, is this function here, let's say f of x is x to the fifth. Is that guy injective, let's see, using the algebraic method. So let's suppose that I pick two x coordinates, I get their corresponding y coordinates, and let's say they're equal. This y coordinate
be squared or
fifth, yes. Sorry. So, someone tell me, does this imply that x1 equals x2?
I think so.
Why do you think so, Victoria? Come on, share with the class. Don't be coy.
I don't know how to explain it.
If that was x1 to the fourth equals x2 to the fourth, would you say it again?
Yeah.
Mr. Jordan there?
I think the only functions with odd degrees can be one-to-one because
Negative.
You can make the negative sign. A negative sign would correspond to a negative value, and a positive sign would correspond to a positive value.
More or less, yes. If I have if this is a polynomial, or just an x being raised to an odd power, then anytime you take the odd root, you're only going to generate one possible value. So this is yes. That's using the standard algebraic definition of injectivity. Does it make sense? Any questions?
Would another way of finding it be just using a horizontal line test?
Exactly. That brings me to the other account of injectivity. These are really all interchangeable, but just different ways of looking at the same thing. So the other account, of injectivity is a graphical way, as Mr. Jordan said. So, in your notes, go ahead and write down the same thing, injective. But now let's do a graphical approach. And for consistency, let's use the same equation we just looked at. Y equals, or f of x is x to the fifth. What does this thing look like in the coordinate plane? Any ideas?
Like x to the third, but even shorter.
Yeah, x to the third, but more sharp, more exaggerated. So it's like a snake, but it's snaking even more sharply through the origin, yes? So that equals, let's call it our first function that we're going to graph here. Let's say that equals x to the fifth. So, visually you can see for any point you pick, you're only going to have, let's say here, for any point you pick, that y coordinate is only going to correspond to one x coordinate. Does that make sense? So I pick this, then let's say this y coordinate down here was -4. Well, if this is 1 to 1, there's only one x coordinate that generates -4. Likewise up here, if you picked a y coordinate of +4, there's only one x coordinate that generates that +4. And yeah, as Jordan alluded to, this passes what's called the horizontal line test, not the vertical line test. The vertical line test, remind me, determines whether a graph is what?
A function.
A function. Horizontal line test goes a step further and says, okay, we can not only determine whether something's a function, but we can determine whether it's 1 to 1. So you pass the horizontal line through it. If your line is only ever intersecting one point, then it is injective.
Say that again, I'm not understanding.
If you pass a horizontal line through your graph, then if it only ever hits one point,
Okay,
your graph is 1 to 1.
okay.
So for example, someone give me a graph that's not 1 to 1, a classic graph that is not injective.
Y equals x squared.
All right, y equals x squared. This nice upward shaping u. And I'll say this is our second function. So, say this point is 2, 4. Is squaring 2 the only way to get to 4?
No.
No, I can also square what else, Victoria? To get to +4.
-2.
-2. So this graph is not 1 to 1. It's 4 equals 4, but 4 equaling 4 doesn't mean x1 has to equal x2. So -2, +4. So if it's injective, it must pass the horizontal line test. So if I pass a horizontal line through the parabola, then you see I'm hitting 2 points
Yes.
all the time, except for the vertex. That's the only time I'm hitting just 1 point.
Right.
Cool. All right, and so those are the two ways from algebra that you guys use to determine whether something's 1 to 1. You probably focused more on this graphical approach, yes? But there's also the standard definition, algebraic definitions. But now with calculus, we have another, and arguably more powerful way of determining whether a function is 1 to 1. So, in your notes. One more account of injectivity using calculus. Is like so. So I'll put the graphs on the board just to start, but you don't need a graph to do this process. So let's see here. Let's say I have a function that goes like this. We'll call that the third one. What do you think that graph is? If I were to flip this above the x-axis, it would take on what shape?
Oh, y equals the square root of x.
Square root of x if it's in the first quadrant, in the fourth quadrant.
So that'd be negative square root of x?
Yeah, negative square root of x. What is this guy doing?
Negative 3?
No, thank you. But I mean, listen to what I mean,
Okay.
not what I say. But also you should listen to what I say too, so I can correct it.
I didn't even see that.
All right, do you see it now?
Yeah.
Okay. Starting from here and working away from right to left, what is this graph always doing?
It's gradually getting smaller and smaller.
Yeah, it's always decreasing, always getting smaller and smaller. And something that's always getting smaller and smaller, do you think can that ever be not injective?
No, it's always
It's
injective.
always injective. It's always decreasing over its domain.
When you say getting smaller and smaller, what do you mean?
I mean, just it's always decreasing from left to right. For example, just like a line. Let's say the line y equals x. That's always increasing from left to right. Yes?
Yeah.
You can have stuff like this that always decreases from left to right. Sure, it decreases at a slower rate the more you go on and on.
Okay.
But it's still nevertheless always decreasing. Let's see. Oh, let's use a nice y equals x squared again for another graph. Call that F2. And let's do one more snaking through the origin. We'll call that F1. I'm really not sure why I went backwards from 3 to 1. But hey, the more complicated thing gets the rarer number. All right. So, is x cubed 1 to 1? Is it injective?
Yes.
Is x squared injective?
No.
No. So we knew that from the previous side of the board. Now let's look at this in terms of calculus. What is the derivative of f3? What's the derivative of negative square root of x? Negative x to the 1/2 power.
It'd be negative 1/2 times 1 over the square root of x.
3 over 2.
Well, x to the negative what?
Negative.
3 over 2, right?
No, negative 1 over 2. X to the negative 1 over 2.
Mm.
No?
Oh yeah, never mind, you're right.
Yeah.
My bad, you're right. No, you're totally right. And that's negative 1 over 2
Times the square root of x.
square root of x. The derivative represents slope, right?
Right.
If something's always decreasing, it always has what kind of slope?
A negative slope.
Negative slope. For everywhere where this derivative is defined, do I always have negative values?
Yes.
Yes. So even if I didn't give you the picture, if you just knew this,
Well, you do have a value of 0. No, you have an undefined value.
yeah,
Okay.
yeah. So over its entire domain, except it has 0, but we don't take the derivative on the endpoints. We take it on the open interval of its domain. Everywhere this derivative is defined, it is decreasing. So the original function we'll say always negative. So if your slope is always negative, your original function is always decreasing. If it's always decreasing, then it is what?
It's injective.
It is injective. Yes, sir. Now let's skip F2 for a moment and go to F1. the derivative of f1, so we'll say f1 prime, is what? You.
3x squared.
3x squared. Now, is 3x squared always positive?
Yeah.
It's almost always positive, except for what x value?
X is equal to 0.
Yeah. Always positive except when x equals 0. Yes, ma'am. But the fact that it equals 0 doesn't mean that it's not always increasing from left to right. Still, go over to the shape, go left to right. You are still always on the up and up for x cubed. Does that make sense? So the fact that it's 0 in one place doesn't matter because 0 doesn't represent a transition from increasing to decreasing or decreasing to increasing. As long as it always represents either, the point where it goes from increasing to still increasing or decreasing to still decreasing, we still conclude that the graph of the original, f1, is always increasing. So again, a slight difference from here. Here, this was always negative wherever this was defined. This isn't always negative wherever it's defined, but in this case it doesn't happen to matter because it's still always increasing.
So we didn't take account of the 0 value of f3 of x because it's an undefined point. It has an undefined derivative.
Yeah, it's undefined at 0, so we don't care about it. So, flip side, if it's always increasing as opposed to always decreasing, f1 is injective as well. Now, very last function here, f2. What is the derivative of that guy?
2x.
Yes, that equals 2x. And this can be positive, right?
Mm-hmm.
It can also be negative. And it can also be, of course, 0. And it's precisely at the point where it's 0 where it undergoes a transition from decreasing, negative slope.
The derivative?
The function.
Oh, the function, okay.
The function. Well, no, the derivative is always always increasing. Slope's always increasing.
Right.
But the values of the derivative, they go from negative slope, 0 slope, positive slope.
Right.
So because of that, you have a transition from negative slope to positive slope for the derivative, increasing to decreasing for the original.
Are you gonna put a 0 next to f2 prime is less than?
Oh, I put the 2 in the wrong spot. My bad.
And also, it says f2 prime is less than this is nothing.
Oh, there we go.
Yeah.
So because of this, f2 is not injective. It doesn't pass the horizontal line test. Does that make sense? You?
Yeah.
Okay.
I mean, wouldn't f1 follow those same rules? Like f1 prime is greater than 0, and f1 prime is less than 0, and f of 1 also equals 0.
F of 1 is never negative. So f1 prime is never negative.
Okay.
F1 prime can be 0 or positive.
Okay.
That's it. It doesn't represent at 0. 0 doesn't represent a transition from a negative slope to a positive slope or a positive slope to a negative slope.
Okay, so the key in doing these derivatives is finding when the derivative switches from negative to positive.
Exactly.
Function.
Because if the derivative switches from negative to positive, that means the graph of the original is going from decreasing
To increasing.
to increasing.
Or vice versa.
Yes, or vice versa. Exactly. Yes, sir. So that's what this term injective means. So what does injectivity have to do with a function having an inverse? In fact, it has a very direct relationship. Can anyone guess?
Would a function's inverse have like the flipped injectivity, or would it have a flipped?
Don't think of it in terms of that. Think of it in terms of a function either being injective or not injective.
Okay.
If a function is injective, so let's just pick one of these.
Injective functions would their inverse would be a function, and if something's not injective, then it wouldn't be a function.
Precisely. We can see that visually. Let's say I pick f1, and I want to find the inverse of f1. So that's going to look something like this. In blue. Like so. So this is the graph of the inverse of f1. And that happens to be a function, right? It passes the vertical line test. But now, if I were to do an inverse graph for f2, the parabola, I'll do that in the dotted fashion here, just to distinguish it from the bolded blue. F2's inverse graph is not a function. It doesn't pass the vertical line test. And that's precisely because it had a point. F2 had a point where the graph transitioned from decreasing to increasing or increasing to decreasing. Anytime you have that, it's not injective, it's not injective. That function does not have a corresponding inverse function. Does that make sense here?
Yeah.
Okay. So I'm going to write that out for you guys. Pretty nice. So, if your function f of x is injective, and also just for the sake of avoidance, there's this other condition called surjectivity, but for the purpose of introductory calculus, we're not going to talk too much about it.
What's it called?
It's called surjectivity. It's rather technical, but I mean technically to have an inverse, you need both. But all the functions we're going to deal with have that property, so you don't have to worry about it. Just worry about injectivity. If a function is injective, side point, then the inverse of f of x exists and is denoted like how? How do you denote an inverse function?
Like f negative 1 of x?
Yeah, it's like f to the negative 1. Again, it's not really a power. Like so. Cool?
Yeah.
Alright, I want you guys to try. And you can try this using any of the three methods. Or the first method is the algebraic definition. Second one was the one you guys are accustomed to from algebra, the graphical way. And then there's this new way, the other graphical way. Which I think you don't need a graph to do this, but you have three ways to test injectivity. Try this. Is f of x, let's say it equals, so that's a good number. It's a good thing here. How about 16x to the 7th minus 11x? Is this 1-to-1? Is it injective? I.e., does it have a corresponding inverse function? So, give that a go for about a minute or two. Okay, y'all, how did we feel about this problem?
A little challenging, but pretty good.
Pretty good, pretty good. You over there?
Good.
Good? Just good?
Got it.
Oh, got it. Cool. All right. Let us, so there are three possible ways. Let's walk our way through them, starting with the first one. Do you think the algebraic method would help me? If I replace the x's with x1 and x2 and set them equal? So let's say 16x1 to the 7th minus 11x1. Suppose that were to equal this guy here. Do you think this method's going to help me?
Not really.
No, it's kind of hard to solve for this when you got x's and x to the 7th. Throw them there, yes? Mm-hmm. Okay. Likewise, the second method?
That's a 7 over the first x1, right?
Yes, that is a 7. So, first method, algebraic method, no help. The second method, it would help, but if we had a what?
A graph?
A graph. Do you know what the graph of this is off the top of your head?
No.
No. So let's fall back to the third method, the calculus method. What is the slope at any point Any x coordinate.
We gotta take the derivative, so
So what rule do you have to use?
the product. Not the product
The
rule.
product, but
The power rule.
power rule. So power rule this fellow for me.
Okay, that's 7 times 16, which I believe is 112. X squared.
Next to the power
X to the
6.
6, yes.
Minus 11.
What did you say this was, Jordan? 112?
112. What do you take by 70? Yeah.
X. So these are our slope values. Do I ever have a place where the slope transitions? That's the key. Does it transition from negative to positive or positive to negative?
I believe there's one point where.
I mean, if it transitions from negative to positive or positive to negative at that point, then at that point the slope is instantaneously
0.
0. Is there a place where this guy is
0.
0?
Then
Yeah, I believe it's the sixth root of 11 over 112.
Yeah, let's set this guy equal to 0. Solve for x. And there are actually, two spots. Positive
Yeah.
sixth root of 11 over 112 and negative of the same thing. So is finding a place where the derivative is 0, is that enough to guarantee that the function is not injective? Do I have to do something else?
You also have to find the values where it's negative and positive.
All right. Is f prime ever negative?
yeah.
Yes. For example, if you stick 0 in for x, you get negative.
Negative 11.
Negative 11. So f prime is occasionally less than 0. F prime is also sometimes
Positive.
positive. And where they transitioned, the slope was 0.
0.
So f is not injective, which means that f does not have a
1-to-1.
well, 1-to-1 just means injective.
And it doesn't have an inverse function.
Yes. Does not have an inverse function. Exactly. In fact, if you were to try to graph this thing, it ends up looking like kind of like a sine wave almost, but a sine wave that isn't bounded by anything. There's one repetition of a sine wave. So coming over here, graph of the original. Looks something like that, yes?
Yeah.
Now, if I were to try to reflect this thing across the line y equals x, so let's choose blue for our inverse. Let's see here, what do I get?
Just that tilted 90 degrees.
Yeah. So, oh goodness. So kind of like something like this for this part reflected.
Maybe.
Ish.
Yeah.
Ish. And then for this part in black reflected across this, something like, something like that.
Something like that.
But in either case, does it pass the vertical line test?
No.
No. So this inverse, the inverse of f, does not happen to be an inverse function. It does not pass the vertical line test. Cool?
Cool.
Right. All right, so this process, the process of injectivity, is how we determine whether a given function has a corresponding inverse function. Whether there exists an inverse function that corresponds to the original. But often in math, let's go around the world here again, fitting for a different concept now. Often in math, we're not just interested in whether an inverse function exists for a given function. We want to go further and say, what is that inverse function? Right, so far we didn't talk about what they were, we just talked about does an inverse function exist for a given function. But the next question, we want to be more specific, like what is it? What is it precisely? So something right, from algebra 1, algebra 2, whatever it was, if I were to give you this function here, keep it simple, let's say 3x minus 7, how did you guys find the inverse function of this? Exactly. So again, I mean, this is one-to-one, I'm not going to spoil that, because we can spoil that much. But how did you find the inverse function of this? So first, you instead of f, you just rewrote it as y equals.
And then we'd swap the x's and y's and
Yes.
set the y then.
We swap the x's and the y's.
So x equals 3y minus 7.
Yeah, 3y minus 7, and then what?
X plus 7 is 3y.
Yes, sir. And the final step, well, second to last step.
And then x plus 7 all over 3 is y.
And the very last step was just to replace y with the inverse notation, right?
Yeah.
Inverse function of f is x plus 7 over 3. Now, key thing to note, and this is easy to lose sight of, this y here is not the same thing as this y here. This y here represents f, whereas this y here,
That represents f prime of f. F prime of x, right?
not f prime, but the inverse of that.
Why did I say f prime? Yeah, inverse.
Yeah, f prime, inverse. They're easy to confuse, but yeah.
They both have that little 1 dash on it.
Yes. So in general, generalizing this, what you do is, let's see here. If we have some function y equals f of x, what we just did is we just took the y and the x, we did what to it?
Flip them.
Flip them. X equals f of y, and then we solve for y. Yes?
Yeah.
So this is just generalizing what happened here, but again, like before, here, y is f inverse. It is not f. So always remember that. So that's just it for how you find the inverse function exactly. You do this process, solve for y, solve for f inverse. But now, with this general notation in place, this general structure in place, we can move our way to derivatives. And it's pretty interesting here. We can fall back on what kind of differentiation to solve for dy or dx. So think back to last time.
Implicit differentiation?
Yeah. I mean, we don't usually connect implicit differentiation with all this weird inverse stuff, do we? But no, it turns out implicit differentiation is exactly what we do right here. So we can ddx both sides of this guy. So I tell you what, I'm going to come over here to get more space. What is the derivative with respect to x of the left side of just x?
That's just 1.
That's just 1. What about the derivative of the right side? F of y. So, variables don't match. You're going to fall back on
The chain rule.
precisely chain rule. This is the derivative of f of y with respect to, what am I going to choose as my natural choice for you? For implicit differentiation? I want them to match.
Yeah, so d of f of y? Or d of y? Okay.
Yeah. Derivative with respect to y of f of y times what?
Times dy or dx.
Times dy over dx, precisely. So, see what I got here. The derivative of f of y with respect to y, I can just rewrite that notationally as f prime of y. Yes, do you go to your Victoria?
Yeah.
Cool, great. Now, if I want to solve for dy dx, what do? I do what to both sides? Divide both sides by
F prime of y.
f prime of y, so it's going to be 1 over f prime of y.
Oh my gosh. Okay.
We good so far?
Yeah.
What was it oh my gosh for?
I mean, it's just like a lot
Yeah, I mean, no, the worst thing about this, y'all, is the notation. Okay? But the concepts are really basic and bare boned. Now, I want to get rid of all the y's. I just want something with x's in it. So we noted in this process, at the very beginning, that y was this.
Yeah.
So if I take this and replace it with f prime, sorry, not f prime. You got me off on the wrong track there, Mr. Jordan. If I replace that with the inverse of f. On the right side, I have 1 over f prime of the inverse function evaluated at some general x coordinate. Whereas on the left, the derivative of the inverse with respect to x, I can put this in a prime notation. This is the same thing as this, yes.
What's the exponent up there? What?
That's not an exponent.
Derivative prime?
Yeah, that's a prime, that's an apostrophe, you just mean take the derivative. That basically just means the same thing as this. If you stick f prime in here, f inverse in here, the derivative of f inverse
All over dx?
all over dx just is the same thing.
Same thing as that, gotcha.
But just less clever.
Okay.
This is our all-purpose formula for finding the derivative of an inverse function at a particular x coordinate.
Okay.
Okay? So long as this denominator does not equal what?
0.
Yeah. As long as this is not 0, and if f is an invertible function, and f is differentiable, so we need two things. F needs to be invertible, f needs to have an inverse, f needs to be differentiable, and this denominator isn't equal to 0, then this is true. This is what's called the theorem of inverse differentiation, or inverse derivatives. So that's some theory. Let's put some concrete detail to it. Suppose I argue this function. Let's say f of x is, let's go with x to the third. And I suppose to say find the derivative of the inverse function I'm going to say inverse because it's going to be a function of f of x equals x to the third power. So let us let's start by finding the inverse function of this. What's the inverse function of x to the third power?
The cube root of x?
Yeah. So algebra method, y equals x cubed. Swap x's and y's. X equals y cubed. Y equals x to 1/3. Yes, sir. And that is our f inverse. So the derivative of f inverse is going to be 1 over f prime. That's another thing I need. Let's write down here. What is the derivative of plain old f? U. Plain old f. Here's plain old f.
3x squared.
3x squared. Just power rule that guy. Equals 3x squared. So what is f prime of f inverse going to look like? I just take the x's.
So 3x squared times x to the third, right?
No, I'm taking f prime of something new.
Of something new.
So it's not just x anymore, it's this whole complicated mess.
Right.
But to evaluate that, I just take the x and I replace it with
y? Or-
yeah, y, which in this case was the inverse function.
Yeah.
So remember, if it's not just a simple x, all you do is replace the simple x with all your new stuff.
Okay.
So 3 all times the inverse raised to what power?
The 1/3. To the square.
Square.
My bad.
That gets here, and of course we know, we just found,
That's x to the 1/3.
that is x to the 1/3.
Okay.
So what is x to the 1/3 all squared?
X to the 2/3.
This is 1 over 3x to the 2/3, and we are done with finding the derivative of the inverse function.
Okay.
Any questions?
Is that not the same as just the derivative of x to the 1/3?
It is, yeah. And so you may wonder, what is the point of this theory, right?
Yeah.
If I could just start here. Look, f inverse is x to the 1/3, then the derivative of f inverse is just 1/3 x to the negative 2/3. What was the whole point of this theorem?
Adding more steps to mess up.
Yeah, it's just torment you, make life a little harder than it already is. But no, for real though. No, there actually is there is a use for this formula that you can't get by just finding the inverse function directly and then taking the derivative. So let's see an example of that. So let's go all the way to the other side. So this is going to flip up towards me. Consider this function here. So let's say I have this function here. It's a nice polynomial. F is 1/3 times x to the 4th plus 4x cubed. Now, as it turns out, and you can verify this in your calculator or on Desmos.com, this thing is going to be an invertible function as long as you restrict the domain to being greater than or equal to -3. Okay, it's a function anywhere, but in order for it to be invertible, have an inverse function, gotta have this. So, with that in tow, let's say we want to find the inverse function's derivative valued at 5/3. So this builds off, what Jordan was saying earlier. Why can't I just find the inverse function directly, like we did for f of x equals x cubed, and solve for f inverse prime directly as well? But watch what happens. If we try to find the inverse function the standard way, the way in algebra 2 or algebra 1, we get something that looks like so. Swap your x, swap your y. So 3x equals y to the 4th plus 4y cubed. Any thoughts on this? Any thoughts on how I can solve for y here explicitly, just like we did with the previous problem?
I can't really think of any ways.
Can't think of any ways?
No.
Yeah, there's no standard way to solve this explicitly for y. So our standard way, or the usual way you might think of solving for f inverse directly, that's not going to work in this case. For this case, we need to fall back on our theorem for inverse derivatives. So, the theorem for inverse derivatives, we need two things. We need to know f prime, and then we need to know f inverse evaluated at that particular x coordinate. So, you, Miss Victoria, help me out here. What is f prime? It's going to be 1/3 times what?
4x cubed plus 12x squared.
Yes, ma'am. 4x cubed plus 12x squared. Ooh. Now, so let's go ahead and set this guy up here. I'll set it over here. I know the derivative of the inverse is 1 over what? Jordan, remind me.
F prime of the inverse of f of x.
Yeah, the inverse function evaluated at that particular x coordinate. So again, f prime of the plain old function evaluated at the inverse, evaluated at the x coordinate of interest. All right. If I want to find the inverse derivative, okay, I'm trying to find this guy. I'm trying to find him evaluated at 5/3, yes?
Mm-hmm.
So I can take this x value and swap it out with what?
5/3.
With 5/3 precisely. Now, how can I find this value? F inverse of 5/3 numerically is just the same as asking what x value on the original produces a y value of
5/3.
5/3. So let's translate that sentence into a mathematical statement. Here's my original. What x coordinate on the original?
So 5/3 is y, right?
Yes.
Okay.
generates a y coordinate of 5/3. So I can multiply both sides by 3 to make this a little less intimidating to look at. I still have a polynomial on the right side with a degree of 4, and I also have a term with a degree of 3 in there.
Yeah, it's equals 1.
But thankfully, because we're dealing with nice numbers, you can just look at this and see that x equals 1. 1. And again, think of this graphically. This is an x coordinate of 1 on the original. And since inverting flips your x's and your y's, or swaps the x's and your y's, an x coordinate of 1 on the original corresponds to a y coordinate of what on the inverse graph?
It would also be 1.
Yes, also be 1. Either way you conceptualize it, this thing in here numerically has to be
1.
Has to be 1. So, if my goal is to find that guy, the derivative of the inverse, evaluated at 5/3, what is the last thing I have to do?
Just plug a 1 into the derivative.
Exactly, plug 1 into this guy. So f prime of x. Victoria, help me out. What is f prime?
1/3 times 16.
Yes, exactly. 1/3 times 4 plus 12. Or 16
Over 3.
over 3. Can't forget the 1/3. So, Mr. Jordan, help me out. What is my final answer?
It'd be the reciprocal of 16
3
over
over
3,
16.
Yes.
which is 3 over 16.
3 over 16 is your final answer.
Good.
Any questions?
No? That's good.
So again, big picture idea. This is an example of a problem where you cannot solve it using Algebra 1 techniques. You need to fall back on your fundamental theorem of inverse derivatives. Are we good with that?
Mm-hmm.
Okay, now notice, there's also another way to do this without your prime notation running around everywhere. If I were to start with this function here, not the original, but the inverted expression, where you swapped your x's and your y's. Make a little bit of space here.
I have a question about the notation.
Yes.
Would it be okay if I were to write this on a test or something, instead of f prime, I could just say dy dx, because the f prime and the f to the -1 gets a little confusing.
Yes, as long as you're clear on the fact that here, this y represents
The inverse.
inverse, then you can do dy over dx.
Okay.
For example, dy over dx for the original, that's not, y is there is not the inverse.
Right.
It's the original. But dy over dx for this guy would represent the derivative of the inverse.
Okay.
And that's exactly what I was building up to here. If you want to avoid the bulk of this notation, I can start with that second expression and do what to both sides?
dy dx.
Not dy dx, but almost. I just implicit differentiate.
Yeah.
I ddx both sides. So when I do that, on the left side, what's ddx of x?
Just 1.
1, right?
Yeah.
And that's going to be 1/3 times what?
4y
4y cubed plus 12y squared.
12y squared.
Plus 12y squared. Is that it?
Yep.
That's it? I was taking the derivative with respect to x.
Oh, times dy dx.
Yes. Gotta chain rule, gotta implicit
Yes.
differentiate. All times dy over dx. So, dy over dx. Or again, y here stands for the inverse of f. Dy over dx is going to be, multiply both sides by 3. 3 all over what?
4y cubed plus 12y squared.
Yes, 4y cubed plus 12y squared. Right? And my goal was to find, go back to the notation just for a second. My goal was to find the slope of the inverse at the x-coordinate on the inverse of 5/3, right?
Yeah.
Okay. If the x-coordinate on the inverse is 5/3, what's the y-coordinate on the original?
Also 5/3.
Right. So we'd still have to do that move where we did last time, looking at the original, replacing y with 5/3, and so on for x. But all the same, we get x equals what when we solve for
X equals 1.
Yeah, x equals 1 on the original.
Yeah.
And if x equals 1 on the original, then
Oh, y can just be 1. And you...
So it's 3/16.
yeah,
Yeah. Okay.
x equals 1 on the original means y equals 1
On the inverse.
on the inverse. So is this the exact same thing we got when we just stick 1 in here? Is this the same thing we got using the previous notation?
Yeah.
Yeah.
I think
So-
even less steps too.
Yeah, so you can do it either way. If you're comfortable with implicit differentiation, you can do it this way we just did. If you're not, if you like this prime notation, you can do it that way. But my point to you guys is that you're not notationally limited. You have 2 options. Any questions about that?
No.
Sure, we're good? Okay.
It is a lot though.
It is a lot. Notationally, it's a lot. But conceptually, we haven't actually done so much so far.
Right.
We've just all we looked as far as, hey, what is an inverse function? 2, how do we know an inverse function exists? 3, how can we determine exactly what that inverse function is? And 4, how can we take the derivative of an inverse function at a certain point? I think it's really, quite a lot, 4 things. There is a 5th thing, a last little thing here.
We're not done.
We're not done, we got one more. So we'll go to the other side of the world for our final thing. And we're gonna look at 3 inverse functions in particular and how to find their derivatives. So what do you think, what inverse functions do you think I'm gonna mention here? They're really special. Before calculus, you talked a lot about finding or dealing with what kind of inverse functions. What was the course right before this one?
It was implicit differentiation, right?
The course before calculus.
Oh.
Pre-cal and trig, right?
Trig. Okay.
Where did you see the word inverse pop up in the context of trig?
Like sine and cosecant and
Yeah. Our 6 regular trig functions
right.
all have corresponding inverses. And we're going to look at just the inverse for sine, cosine, and
Tangent.
tangent. So let's start with sine. Y equals sine x. If I want to invert this guy, I just do it. Algebraic.
Swap the variables.
X equals sine of y. We're now getting key here. Unlike before, y is the inverse of sine, yes?
Yeah.
Just like we were doing before. All right. My goal now is to find the derivative with respect to y with respect to x, so I ddx both sides. Someone help me out, what does my left side equal to if I do that?
Left side is just 1.
1, and right side is?
Cos of y times dy dx.
Right. And we can do that in the chain rule, so I'll do this one in full-fledged detail. ddx of sine y is this times this, yes?
Yeah.
What is the derivative of sine with respect to y?
Cos of y.
Right. My variables match. Cos of y. So the derivative of y, where again y here represents the inverse of sine, is going to be 1 over. On the right side, I have cosine times dy dx. So dy dx by itself is 1 divided by that. 1 over cosine y. But now I can simplify this even further into something very, very nice and unexpected by noting the following. whatever y happens to be, what does sine squared of y plus cosine squared of y always have to be equal to?
1.
Always has to be 1, yes. So, cosine squared of y always has to equal
1 minus sine squared y.
1 minus sine squared y. So, cosine y is going to be the square root of that guy. And it's going to either have a plus sign or a minus sign. Okay, so I have one of those. But I'm taking the cosine of y, yes? And y is inverse sine. Does anyone remember from trig what the restrictions are for inverse sine? Inverse sine always has to be sandwiched between what two values? Anyone remember? The way we define inverse sine as a function in trig is that it's always in between negative pi over 2, fourth quadrant, and
Positive pi over 2?
positive pi over 2, yes. That's just a little recap from trig. In other words, I'm always in either quadrant 1 or quadrant 4 when I'm dealing with this function. Now, if I'm in quadrants 1 or 4, for inverse sine is y, and I'm taking cosine of y, I'm always taking cosine of an angle that's in either quadrant 1 or quadrant 4. But what's cosine of anything in quadrant 1 and quadrant 4? It's always going to be
Positive.
always positive. So I choose the positive roots. So I have cosine y equals positive 1 minus sine of y. I'll just change this to the whole thing squared. And this guy, if I replace y with inverse sine, I get 1 minus sine of inverse sine of x, all squared. But what is sine of inverse sine always equal to? Sine inverse sine of x.
Well, sine of inverse sine?
Yeah, sine of inverse sine of x is always
1, not
not
X.
1. Yeah, it's just always x. The regular thing and the inverse cancel each other out, so to speak. So that's always x. So cosine of y always equals square root of 1 minus x squared. So I take this thing, I smuggle it in right here, and I get something very unexpected. Unlike your derivatives for plain old trig functions like plain old sine, plain old cosine, plain old tangent, which had a trig function in your derivative, for the derivative of inverse sine, as it turns out for other inverse trig functions as well, you can express that derivative in terms of just quadratics and square roots. Actually, I'll write it out as a formula. So the derivative of inverse sine of something is just 1 over the square root of 1 minus x squared. So you don't see any weird trig stuff in there, do you? Just an x and square roots. Any questions?
That's the inverse derivative. Right?
That's the derivative of inverse sine, yes.
Inverse sine, gotcha.
And let's see here. And on your own, sometime, you can also prove this one. Again, using exactly analogous argument, exactly parallels this argument, as it turns out the derivative of inverse cosine is the same thing, but with a negative sign in the denominator. So that's another formula. So here's the formula for inverse sine. Here's the derivative formula for inverse cosine. Now I want you guys to take a minute to try proving the derivative formula for inverse tangent. So, did anyone manage to prove this fun guy?
I think I got it.
You got it?
Maybe.
All right, I'll come up here and demonstrate. I'm quite tired of writing.
Okay. So we're trying to prove what again? Trying to prove.
We're trying to prove that the derivative of inverse tangent
Okay.
is equal to something. We're trying to find what that derivative is.
So we got. Let me just erase this. So our f of x is just tangent of x.
Yeah, just plain old tangent.
I should have said y instead. because in order to find the inverse, we're gonna have to swap the two.
Swap the x and the y,
So
precisely.
x equals tan of y.
Yes, sir.
And then we gotta take the derivative of both sides
With respect to?
with respect to y.
No, with respect to
x.
Yes.
Okay. So then I will do d dx of both sides. And d dx here. So this just becomes a 1.
1.
And then by using the chain rule here, you will
Yeah.
get secant squared of y
Times.
times dy over dx.
Yes, sir. Precisely. It's just implicit differentiation.
Okay. And then with that, so dy dx is just 1 minus secant squared.
Minus.
Oh, I messed up. I did the same mistake while working on it before.
That's third time.
That's a multiplication sign. So that's 1 divided by secant squared of x. And that's dy dx.
Secant squared of x.
Of y. It's the morning.
It is the morning.
Okay.
Secant squared of 1.
Now that we have that, we can use a trig identity, right?
Which one?
There's one trig identity that says tangent squared of
anything.
anything,
Which is
let's
called
say
y.
will equal secant squared
Secant squared
of
minus.
y minus 1.
So then secant squared by itself.
So secant squared by itself would just be tangent squared of y plus 1. So with that, you can. That's a plus sign.
I don't know. That was like an H. Erase that.
I'll
Make
erase
it.
that H.
Make it more aesthetically pleasing.
I criticize you for your handwriting. I should not be a hypocrite. Okay.
Nothing worse than that.
There we go. So, now that secant squared of y is tan y plus 1, I can do the substitute thinger and just do
The
that.
substitute thingamajig.
Yes. And I'll go ahead and write here because you knocked there. So dy dx equals 1 over.
No, rewrite that. What in the world?
I'm quite sleepy. I am sorry. 1 over tan squared y plus 1.
Plus 1.
And now we can take the
What does y stand for?
y stands for tangent of x, right?
That was before
That
the
was
swap.
before the inverse.
After the swap, then y stood for.
Y stood for well, tangent of y was x, so then x would be the inverse tangent. Well, y would be the inverse tangent.
After
of
the
x.
swap, yes.
After the swap, yes.
So you can get rid of
So I can say that equals. Okay, I can make my life.
You have this whole
more
space
small.
here. Yeah.
I promise. Okay, so that equals 1 over tangent of inverse tangent of x, and that whole thing squared. Let's make this longer.
We want another parenthesis, don't we?
Plus 1. Another one?
Yeah, the way it looks like, just to emphasize, you're squaring that entire
Like that?
thing. No, after right before the 2.
Like here?
Yeah.
Okay.
No, right before the 2, we need a parenthesis. We're squaring that entire thing.
Oh, so like this whole thing.
No,
It's
this entire thing.
oh, the
Squared.
entire thing squared. Okay.
So we'll edit that out.
This is gonna be fun to edit. Wait, do I put the 2 there?
If you do this, it looks like you're just squaring the input.
Gotcha. So I'm gonna take this entire thing and square and plus 1. So now we can see through here that tangent of inverse tangent of x is just gonna be x.
Right, but what do those two things do? Tan and inverse tan.
They cancel out. They're reciprocals.
Oh, reciprocals, so they're inverse. They offset each other.
They offset each other. So sorry by saying they're inverses. Okay. So then that last thing will just be, since that kind of just does that, it will just be x, and that whole thing is squared plus 1.
Yes, sir. It is a nice quadratic. No trig functions in there. Just nice polynomials, and there we go. That is the derivative of inverse tangent. So go ahead and write that here.
Okay.
So d dx of inverse tangent.
Dx of tan inverse of x.
Is that right there? Yes. Go ahead and box that or flower cloud that, whatever you want to do.
I'm gonna flower cloud it in blue, like a nice spring cloud. That looks like a cloud. There we go.
Looks like a foot with a lot of
That's a lot of toes in a foot.
pustules on it.
That's gross.
That's fine. Either gross or not. Come here. Come here.
Yay, brotherly affection
There.
caught on camera. Is that it?
That's it.
Cool.